Let's prepare on thin cylinders. So first, what is thin cylinder? So thin cylinders are nothing but it is a simple cylinder only, but its thickness is very small. Okay, so the thickness of the wall of that cylinder should be less than 1/20th of its diameter. So that much thinner the thickness of that shell should be. Okay, so here some stresses are occurring. So the normal stress occurs, that is sigma h and sigma l, that is nothing but the hoop stress and the longitudinal stress. So let us see now how the stresses are occurring. So if you take a cylinder like this, so I am taking half of the cylinder like this. Okay, so the pressure will be acting like this. In all the radial actions, the pressure will be acting, so that the hoop stress will be acting along the circumference of that cylinder. Okay, so this is the hoop stress, and the longitudinal stress, it acts along the length of that cylinder. So if this is the length, means for example if the pipe extend like this, means along this length the longitudinal stress will be happening. So this is about the hoop stress and the longitudinal stress. So you just imagine a pipe with the water. Okay, so the pressure is acting, so due to the pressure of that water the hoop stress will be followed. Okay, so that's all. So these both are only normal stresses, and the radial stress here is very small, so that it is neglected. And then the bending of the wall of that cylinder is also neglected. So these are the assumptions to be noted. Okay, so circumferential or hoop stress means it is denoted as sigma h, which is equal to P into D by 2T. So this P is the pressure in the pipe or that cylinder, D is the diameter of that cylinder, and T is the thickness of that shell of that cylinder. Okay, so this both hoop stress and the longitudinal stress both will be in a tensile form only, and if some efficiency of that pressure of that cylinder is given, means you should divide the formula by that efficiency value. Okay, if it is a longitudinal stress, means it is PD by 40. Actually this is formed by equating the equilibrium conditions of the force acting along the shell like that equations and all is not necessary, so we can directly study this formula, it is enough. So for hoop stress it is PD by 2T, for longitudinal stress it is PD by 4T. So from this you get a relation that the hoop stress will be equal to twice the longitudinal stress. Okay, so this is an important point to be noted. And this P value, so this P value is the pressure. So if in the question, if they are giving the pressure head of the pipe or pressure head of that cylinder is this much, like that, means you should not apply that value directly. Okay, so here pressure means it is the stress. So pressure, it is the unit is kilogram per meter square, whereas the pressure head of water, the unit is meter only. Okay, so just for example I am telling you, if water is passing through a pipe having some 100-meter head is allowed, means then the pressure value, it should be multiplied with the density of the water. Okay, so the density of the water, we know it is 1000 kilogram per meter cube. So 1000 kilogram per meter cube into that 100 meter of the water. So you will be getting 100 into 1000 in terms of kilogram per meter square. So this is the pressure value you should substitute for P in this formula. And the next is the strain. So here it is hoop strain, which is equal to sigma h by E minus mu into sigma L by E. So E is the Young's modulus of elasticity and mu is the Poisson's ratio. And for longitudinal strain, it is sigma L by E minus mu into sigma h by E, just the inverse of this. Okay, so just they have exchanged the h and L here. So I have expanded this in terms of that PD value, because we have for sigma h and sigma L values, no? So that I have substituted here and I have written. So this may be easy for you to substitute the values directly and find the answers. Okay, and the volumetric strain is this PD by 2T into 5 by 2 minus 2 mu. And the maximum value of shear stress, so normally the shear stress will occur in any element. So in this particular thin cylinders, the maximum shear stress will be half of the hoop stress. Okay, so it is sigma h by 2. So that is all about the thin cylinders. Now we have come for the thin spherical shells, where the element is in a spherical form. So here, due to the spherical form, the longitudinal stress won't be there, only the hoop stress will be there. So hoop stress will be equal to PD by 4T, and if efficiency given, it's divided by efficiency. Here the maximum shear stress is equal to 0. Okay, so this is an important point. They have asked this many times in the exams. And the strain formula, only it's hoop strain here. So sigma h by E minus mu into sigma h. Again, I've expanded here and written like this. And here the volumetric strain is 3 times the hoop stress because it is a spherical shell. So it is all the 3 directions into the hoop strain will give you the volumetric strain. Thank you and keep watching for the next lecture on columns and struts.